Okay. Am I audible?
Yes,
Yes,
you are
you
audible.
are.
I think
Yeah,
inside our institute there is a network issue.
okay,
Not
okay, fine.
disconnected. Okay, yeah.
Sure, sure. No problem. Okay, this is just an anecdote where Dijkstra says how he came up with this algorithm. He was waiting in a cafe and like he thought about this in around 20-25 minutes, is what he says. It's just some anecdote where yeah, he was sat waiting at a cafe and then he was thinking, etc. etc. Right. So this is the code once again. So what we are doing is every time we are extracting the one with the least the smallest priority value, and you look at its neighbors. So this is the neighborhood. N of u is set of neighbors of u, right? Set of, maybe I'll just say out neighbors of u, right? And what you are doing is repeatedly doing this step. You look at the d value of u plus the weight of the edge from u to v. Is it smaller than the d value of v, the existing d value of v? If so, you update the d value of v to be this, and yeah, you update the d value of v, and you also uh, update the parent pointer, right? So basically, there was some way in which you reached v earlier. Now, if the current way is shorter, the current way meaning through u is if it is shorter, then you update the d value of v and also the parent pointer of v. That's all that you're doing. In fact, almost all of the shortest path algorithms have this kind of step at the heart of it. Like not just Dijkstra, but even if you have negative ways, or if you want to do all pair shortest paths, where like for all the pairs of the vertices x and y, you want to find the shortest path from x to y. Because yesterday I said this is single source shortest path. From a single source, you're computing all the shortest paths. In all the cases, all the shortest path algorithms, we essentially do this kind of step repeatedly. It is just the way in which we do this step, in the order in which we update. These are the things that differ. But this is a standard step that you do. Basically, if you have a vertex u and if you have an edge v, what is the shortest way to get to u plus the weight of the edge uv? If that shortest way to get to you plus the weight is smaller, then you update the V's entry. And this has to be done repeatedly. This kind of process is at the heart of, if you study any shortest path algorithm, this is what you will see. Like this will be there somewhere inside. Okay. Any questions on the algorithm?
So what does decrease key perform here?
I'm sorry, what is the?
What does the operation decrease key?
Oh, basically, okay, maybe it is just saying that in the priority queue, you update the d value of the entry. So yeah, I understand that this is already looking like we do that, but I'm just explicitly writing it so that we see this thing happening. Yeah. So maybe this and this are the same thing. Yeah, we don't need to separately write it. Yeah, it's not doing anything extra. Any other questions? Everything is clear of the algorithm? Okay, good. Now I will very quickly go through the proof. The proof is similar to the breadth first search proof, so you can read it on your own. But I'll just quickly go through it. Before that, the running time. So maybe this helps to go through this. So all these steps take around O of V time because you have to assign these values for all the vertices, right? Yeah, so we initialize this priority queue, all that. Then we do extract minimum. How many times do we do extract minimum from the priority queue?
3 times.
V times, because every time you extract the minimum, it never goes back into the queue. So this is done V times. And how many times do we do this decrease key?
For each time, number of neighbor, which is maybe degree of that vertex.
Correct. So it's basically degree. You're adding the degrees. So for each vertex, it's like for each vertex, how many neighbors it has. We may not do it for all neighbors, but the upper bound is all the number of neighbors. So summing it up over all the vertices, when you sum up the degrees, you get the number of edges. Okay. Assuming it's a directed graph. If it's an undirected, you will get twice the number of edges. So decrease key is done at most E times, right? So yeah, so this is what this slide says. So assuming it's directed graph, assuming directed graph. I think even if it's undirected, we will not be doing more than E decrease keys, I think, because like once you DQ one, you will not see the other one. Anyway, I just say this. So we need to do V decrease keys, V extract mins and E decrease keys. And the question is, how do we implement this priority queue? So we need some data structure to implement this. You could simply have an array of values. So there, decrease key would be easy. You can just look at the entry of a vertex. Like the priority queue could just be an array. Right? It could be just like array means something like this. You could have an array of, let's say, V1, V2, V3, and so on. And you have the key values, let's say 3, 5, 10, 2, 6, something, right? So now decrease key is easy because you just, if you want to update the key of this, you just go here and decrease. But then extract min takes time because you have to search this entire array and find the smallest value. So extract min takes V time. So there are other ways to implement it. So if it's an array, then the running time will be V times V, because we do V extract mins. So V times V and E times constant. So it'll be, if it's array, the running time will be, sorry. I'm sorry, just give me a moment. Yeah. Am I audible and visible? Everything is clear, right?
Yes, yes.
Yeah, okay, thanks. So if it's an array, the running time will be O of V square plus E, because V times V plus E. But there are other ways to implement this priority queues, something slightly more involved and sophisticated. There is something called binary heap, where both of these take log V time. So if you notice that the extract min happens much faster in logarithmic time, decrease key actually increases time because of the sophistication. It takes log V time. So if it is a heap, then that overall implementation will take O of V plus E times log V, right? So this seems slightly better because it's not clear, right? So because V plus E log V, so assuming you have more edges, I think, yeah, it's depending on the actual the density of the number of the density of the graph, meaning the number of edges, it'll be different. Then there is something more sophisticated called Fibonacci heap, where extract min takes log V, but decrease key takes constant amortized time. So amortized time is also, it's like an averaging over many operations. So this takes O of V log V plus E. So this is strictly better than our this one is strictly better than the array implementation, right? So that's the time complexity of Dijkstra. So it really depends on how this priority queue is implemented. Okay, any questions on this? Okay, I'll quickly talk about the proof of correctness. I'll not spend too much time. So the statement is that at the end of the algorithm, we have for each vertex, the d value is equal to the shortest distance. So where this delta SU denotes the length of the shortest path from S to U. Okay, this is the claim. Right. So what we do is we take the first vertex that is DQ'd. Maybe I'll just say first vertex to be DQ'd, for which the d value differs from the actual shortest distance value, right? Take the first vertex which is DQ'd such that this does not happen, right? So in the ordering, the claim is that let's assume for the sake of contradiction this happens. Now, if the vertex is not reachable from S, then d value will never get updated because d value of U never gets updated, and the shortest path length is also infinity. So you should be reachable from S. Okay. And U is also not equal to S because if U is equal to S, then the distance is 0 and the d value is also 0. So U is also not equal to S, right? So U has to be some vertex that is not S but reachable from S. Okay. Now you take the shortest path or take one of the shortest paths from S to U. There could be multiple shortest paths. And so we are at the instance where we are about to DQ U, right? U is the vertex that is the first vertex where upon DQing, the d value and the distance is not the same, right? So in that path from S to U, take some path. Let's say that, like, look at the path. How many vertices are already DQ'd? Maybe some vertices have been DQ'd, maybe some are not DQ'd. Look at the first vertex that is not DQ'd. So S is the set of vertices that are already DQ'd. So now let Y be the first vertex in this path that is not DQ'd, right? And let X be the preceding vertex, meaning S to X everything is DQ'd, Y is not DQ'd, and maybe Y to U, maybe there are some vertices in between that is DQ'd, some vertices that are not DQ'd, I don't know, right? So two claims, both of these claims are easy to show. The first claim is that the distance of Y will be equal to the d value of Y already. Even though Y is not DQ'd, the distance from S to Y, it will be equal to the d value. And the second claim is that the distance of or the d value of U is actually at least the distance. It is not smaller than the distance. It is at least the distance. So these are the two claims. And along with that, notice that this is the shortest path from S to U. So even the path from S to Y is the shortest path from S to Y. Why is this? I claim that this path, whatever path this is, from S to X and then X to Y, that's the shortest path from X to Y, S to Y. Can somebody tell me why this is the case?
So if we have another shortest path from S to Y, then we can go from S to Y first, then we can come back to X. So this will contradict that sigma 1 is the smaller path from
Can
S
you
to
please
Y.
repeat? You can go from S to Y and
Then we'll come back.
we may not be able to come back because the YX edge may, if it's a directed graph, this edge may not exist. But you can get some other contradiction. Till that point, the argument, can you do some other contradiction? If there is another shorter path from S to Y, then we can take that with sigma 2 and get a even shorter path from S to U. This contradicts the fact that we started with the shortest path from S to U. So you don't go back from y. Instead, if there is a shorter path from S to y, you can start from that path and go from y to u using sigma 2 and get a shorter path from S to U, which contradicts that sigma was the shortest path from S to U. So all the subpaths in this path must also be shortest paths. Because if anything is not the shortest path, then you can shortcut it and get an even shorter path. Okay. So that gives us this. So we have three things. One is that dy for y, the d value is equal to the shortest path length. Two, the shortest path length of y is at most the shortest path length of u. Notice that we are using the fact that the edge weights are non-negative here, right? Because like otherwise, if the path yu has a total negative weight, then we cannot say this thing, right? So even though I'm saying it rather quickly, the assumptions are being used. And the third thing is that the d value of u is not smaller than the shortest path length, right? Now, if you combine these three things, this, and this, you get the following series of equations or inequalities. dy is equal to delta sy, which is at most delta su, which is at most du, right? So which means dy is less than or equal to du is what we get. But we started by saying that just before u was dq'd. Now, why was u going to be dq'd if dy is less than or equal to du? The only way this can happen is if both y and u have the same d value, and then you arbitrarily picked one of them, right? So the only way this can happen is if both of them have the same d value, which means all these inequalities have to be equalities, right? But if they are all equalities, then that means that du is equal to delta su, which I think is what we want to show. So except for the proofs of claims 1 and 2, we have shown that whenever a vertex is dq'd, meaning extract min from the priority queue, the d value of that vertex is equal to the shortest path length. Is it clear in the proof? There are questions, please ask. We just have to prove claims 1 and 2. I will probably just share the slides because these are really basic things. But except for these, the statements of claims 1 and 2, is there anything else that that is confusing or unclear? Okay, so I'll go ahead. I'll just maybe quickly show you the slides. So claim 1 is that dy is equal to delta sy. That is because x is already in the in the x is already dq'd, and we correctly identified the shortest path distance from s to x. And when you update the d value of y from here, then this also gets updated. That's basically what we have written here. And this is also simple. The d value of u is never strictly smaller than the shortest path distance, because whenever we update the d value, we update it when we have a path of that length, right? If you remember the graph on which we ran and executed the Dijkstra's algorithm, whenever we updated the d value, we actually found a path of that length. So every time the d value is updated, let's say to 10, then there is an actual path of length 10. So which means the shortest path cannot be more than 10, but it can be less than 10 because some other path could have existed that we haven't seen. But it cannot be that the shortest path is like length 15, because whenever we do a d value update, we actually have a shortest path of that length. Right? So that's basically the proof of claim 2. Okay. So with that, I would like to stop the discussion on the shortest path algorithm, Dijkstra's algorithm. Any questions on Dijkstra's algorithm? Just once more, I want to just stress this point. The key step here is this step. If u is already like dq'd, and you check the distance of u or the d value of u plus the weight of the edge uv. You check if you compare it with the dv, and if it is smaller, you update the d value of p and and the parent pointer. And this step is sometimes called relaxing, I think, or relaxation. I think this is what we are referring to in this step, right? Yeah. So any shortest path algorithm basically will have this relaxation, this repeated relaxation, not just Dijkstra's. Okay, so I think if there are no questions, shall we move to the next topic? Okay, so yeah. Okay, so we have maybe slightly less than an hour, 50 minutes. I think in the original schedule, I said two more topics, minimum spanning trees and max flow min cut. But I don't think I have time to do both. So I'll just talk about max flow min cut for how much ever time we have. So it's a very interesting topic, right? So I'll tell you what flows are, what maximum flow is, and what is minimum cut, and then something that is a connection between both of them. So this is just a bit of history. In 1950s, so researchers from the US defense organizations, they wrote some report about the railway network in the then Soviet Union. So earlier, this countries that are Russia and the surrounding countries were something called Soviet Union, and this railway network was modeled as a graph. Okay, so in 1950s, not very far from, or not very much. It's still people are like, I think the World War II was just fresh in people's minds. So the railway network was represented as a graph which had like many 44 vertices and 105 edges. So they were studying, the researchers were studying what is the maximum amount of material that this railway network can carry from, let's say, one side from the east to the west, or from the west to the east, right? It's like how much of quantity can be carried from one side to the other. Another question that people looked at is, like, I want to, let's say, disconnect the east from the west, meaning east, meaning the Russia from the rest of Europe. What is the easiest way I can disrupt this train network? Meaning, I want to like, let's say, in a war, you want to just destroy some railway lines so that the network gets disconnected. And destroying a railway line involves some cost, right? You have to carry explosives, or you have to carry troops, and basically involves some cost in terms of manpower, equipment, investment, and so on. So everything is valuable. What is the cheapest way in which you can do this, right? So this is kind of this was kind of an example of a max flow min cut problem. And when I define the problem more formally, max flow and min cut, you'll see the connection. Okay, and this is one of the first instances where it was recorded, even though it's kind of encoded as some other terms. Okay, so here we have a directed graph. So first I'm defining max flow problem, and we have two vertices S and T. Okay, these are special vertices. So S is the source and T is, I think, target, I think. And you have capacity functions on each edge, right? Okay, and so I'll and all these capacities are positive, okay, no, or non-negative. We want to assign flows on each edge. Okay, so what are flows? Flow is some value that is positive, meaning Flow is some value that is non-negative. For each edge, you want to assign flows. So flow should be non-negative, and flow is upper bounded by the capacity. So if an edge has capacity 10, you cannot carry like 15 flow. Okay. And we also have this flow conservation property. If V is any vertex, the total incoming flow, which is the left-hand side, and which is also depicted here, is equal to the total outgoing flow. So one way to think about these flows are um, one way to think about these flows are like, think of it as some flow of water or something, and these are pipes. Okay, the capacity is saying how much, what is the maximum water it can carry, or maximum, let's say units, maybe how many liters can it carry per every second or something, right? So if the pipe is wider, it can carry more water. If the pipe is smaller, it'll carry less water, right? And when you have a junction of these pipes where you have multiple pipes coming in and going out, all the water that comes into the junction should be able to leave the junction, right? So that's what the flow conservation is, right? If you have some junction where more water comes in and water does not have way to go, then there will be something, pipe will burst or some leakage will happen, right? Right. So, and you simply cannot have less water coming in and more water going out, because there is no water, there's no more water to go out, right? Right. And one point is that the flow conservation at each vertex. So this is the flow conservation. This is true, or we want this to be followed only for all the vertices except the source and the sink, source and the target, S and T. So S and T are kind of special vertices. So we want the flow conservation to be true only for all the vertices except S and T. Okay. And given these conditions, right, we want to maximize the flow of the network. What is the maximize? What do you mean by the flow of the network? I want to maximize the outgoing flow from S. Okay, so which is the net outgoing flow is the total flow going from all the edges from S minus all the total flow coming into S. And we want to maximize this. Just to see if you're understanding, if you replace S with another vertex V here, what should be this value? What should be this quantity? If we had V instead of S here, this quantity, if you replace S with any other vertex V in the graph, what should this be?
Zero.
It is zero by just what we just said here. By flow conservation, the total flow outgoing for any arbitrary vertex is equal to the total flow incoming. So this will be zero. So for S, we don't want to impose flow conservation. And also T, we don't want to impose flow conservation. That's the reason why we don't want to impose flow conservation. So this is called, okay, we'll just say that in a moment. So this is called the value of the flow. Okay, now it can also be shown that the same value F, the same F is the net total incoming flow to T. So here I define it as total outgoing flow from S minus incoming flow to S. But it can also be shown that this is equal to total incoming flow to T minus total outgoing flow to T. This is simply because if you take the graph as a whole, everywhere there is flow conservation except S and T. So whatever extra is produced at S, it has to be consumed at T, because if there is otherwise it will be like, yeah, so because the graph is a closed thing, the flow only happens across vertices of the graph. So everywhere there is flow conservation. So whatever was produced excess in S, whatever is net extra outgoing from S, this has to go into somewhere, right? And you cannot, no other vertex is absorbing. So it has to be absorbed by T, which is the only other vertex where we do not have to have flow conservation. Yeah, so I think I've written the same thing here. Yeah. Okay, maybe now that we have defined everything kind of in notation and grammar, we will see some example. So this is one example, right? So what I've written here is S and T are there, and the red letters are the capacities of each edge, and there's all the edges are also directed. One example of a valid flow is this. So you can see now this vertex total incoming is 10. So the blue is the actual flow value. So notice that 10 is less than 20, 10 is positive, 10 is less than 20. So it's a feasible flow. So any flow is said to be feasible if it satisfies these conditions, right? This condition and this condition. We say that a flow is feasible if it satisfies these conditions. So 10 is less than between 20 and 0. And here the H has capacity 10 and the flow is also 10. So 10 is at most 10 and greater than 0. Here also capacity is 10, flow is 10. Here capacity is 15, flow is 5. Capacity 10, flow is 5. Capacity 20, flow is 5. And wherever I have not indicated anything, the flow is 0. Okay. Okay. So whenever I have not indicated, flow is 0. Flow 0 in edges where no flow is indicated. Okay. So we verified that each edge meets these constraints. So we basically verified condition 1, right? We can verify conservation condition also. So we look at this vertex, incoming is 10. Here there is nothing outgoing. Here the outgoing is 10. So incoming is 10, outgoing is 10. This vertex, incoming is 10, outgoing is 10. Nothing incoming from here and here. This vertex, incoming is 5, outgoing is 5. And this vertex, incoming is 10, outgoing is 5 plus 5, 10. So flow conservation is met at all these 4 vertices. This is S and T, so we don't do flow conservation here. What is the value of the flow? What is the value of this flow?
Ten.
It is 10, right? Because we define the value of the flow as a net flow outgoing from S. So total flow outgoing from S minus total flow incoming. In this graph, there is nothing can come into S because S has basically only 2 outgoing edges and no incoming edges. So it's like flow in this edge plus flow in this edge. The bottom edge, there is no flow. So it's just 10. And you can also verify that this is equal to the net flow incoming into T, because here it's 5 and here it's 5. So both ways we've just basically verified the value is 10. The value of the flow here is 10. Right? So is the definition of flow clear?
Yes, but can we have incoming flow to the source?
You can have, but usually like for the sake of definition, I included that. But what we are going to define now is a maximum flow problem. So once we define the maximum flow problem, then you'll see that it doesn't make sense to actually, in this graph, there are no edges, incoming edges to S. But once we define the maximum flow problem, you'll see that even if there were incoming edges to S, it doesn't make sense to, when the goal is to maximize, there is no point in sending flow to S because it doesn't really serve like it is not contributing to the maximization, right? Because it's only decreasing the net flow. So even though I defined it that way, typically in the examples or instances that we see, there will be no incoming edges to S itself. And likewise, no outgoing edges from T also.
Okay.
Yeah, but we can have it. It doesn't change the. It doesn't hurt. Yeah. Okay. Any other questions? So now the maximum flow problem. So this is a flow, right? The question is, so what is it? The maximum flow problem, as you may have guessed, is to maximize the total flow from S to T. So can we send more flow in this graph? Can you suggest something?
We can, like from the source, if you increase 10 to 15, and then 5 flow can carry over from there in 5 years. So there is excess
We just add a
capacity. So
page here, and then we can. So maybe I just take this. Okay, so what we are suggesting is to add 5 where from to the, maybe I'll just label these vertices, say A, B, C, D. You add a flow 5 where?
instead of 10, the first from S to A.
S to A, you want to make it 15, okay?
15.
Now you have to have flow conservation at A. So you send
So
5 over here
5.
because there are only 2 outgoing edges. So you have to send the 5 here. And now you can
From B to T again 5 add. You can
add 5.
10.
Yeah. So now you've increased the flow from
Yes.
10 to 15. Yeah. And you can verify that that it is still meeting both the requirements. That is, every edge it is at least 0 and at most the capacity. And every vertex there is flow conservation. So you can just check this vertex, it's 5 plus 10 is 15, and here it is 5 plus 5 is 10. And these two vertices, I don't think we changed anything, so it still remains so. So we can, now we have a flow of, so here flow value is equal to 15. Okay, can we increase it further?
No, because then the capacity for C, that will be exhausted. Because if you send more than 15, it cannot outgo from A. We cannot send more than 15. So that side.
So from A, yeah. So let's see why we cannot send more than 15. So if we send more to this edge, certainly A will not be able to supply more than 15. So we cannot send more than that. What about here?
That also not possible
This
because
edge basically it is empty, so you can send more. But then
C
it has
will
only
not
one
be able
outgoing edge, which is also full. So basically, this edge and this edge, these three are full, and they are kind of preventing us from sending more, right? So this kind of reasoning is what we need in this problem, and we will see that kind of thing. So in this case, the maximum flow is 15. All right. Any questions on this example? Everyone else is clear? If you have questions, feel free to ask. Don't have to feel shy about it. Okay. So now we will talk about the minimum cut problem. Okay. So again, we have a similar graph with designated S and T. In fact, we'll use the same graph as example. And you have capacities on the edges. An ST cut. Okay. So an ST cut is is a partition of the vertices into two subsets, capital S and capital T, such that small s belongs to capital S, small t belongs to capital T, and it's a partition of the vertices, meaning all the vertices S and T should together together contain all the vertices, and they should be disjoint. So basically, you divide the set V into two parts, capital S and capital T, such that every vertex is there in either S or T, but not both. And further, we want smallest to be in capital S and small t to be in capital T. Right? This is an ST cut. An ST cut is two sets, capital S and capital T, such that S and T fall into capital S and capital T respectively, and all the vertices are in one of them. Right? And now the capacity of this cut capital S capital T is given by the sum of all the edge capacities that are going from S to T. So the capacity of ST is denoted like this, ST with these double lines in both sides. It is given by, you look at all the vertices V in S and W in T, and basically, which means these are edges these are pairs of vertices that are crossing the cut. So S is here, T is here, V is here, W is here. Add up the capacity, all the capacity of such edges. So there could be multiple such edges. You add up the capacities of all these edges that are crossing the cut, right? So this part is important, that are crossing from S to T. That is the capacity of the cut. The capacity of the cut is the sum of the capacities of the edges that are crossing from capital S to capital T. Notice that there could be edges that are going from T to S. We don't bother about them. The capacity of ST is only defined. So it's not like S and T don't have symmetric roles. S is on one side, T is on the other side. So we only bother about the capacities of the edges that are going from S to T, not the other way. Okay. And that's what it is. So some examples. So this is the same graph. So the green part is the light green part is the set. The same graph with same capacities also. This part I'm calling it S, and this part I'm calling it T. So notice that small s is in capital S, small t is in capital T, and all the vertices are there in one part and only one part. There is no intersection. They are disjoint. Right? What is the capacity of this cut?
$15.
It's 15. It is 15 because there are three edges that are crossing the cut, out of which one of them is coming from T to S, so we don't care about that. There are two edges that are crossing, that are going from S to T. One is this edge and one is this edge. So 5 plus 10, the capacities of these two edges is the capacity of the cut. It's 15. So the minimum cut problem, so this is the cut and the definition of the cut. The minimum cut problem is given a graph with capacities and designated vertices S and T. Find the cut that has the smallest capacity. Is the definition clear? Are you clear about what the max flow problem is and what the min cut problem is?
Yes.
Okay. You've been answering, so I know you are following. I hope others are following too.
Yes, sir.
Yeah, thanks. Yeah, maybe one other example we'll do. This is another graph, okay? And the red ones are the capacities. I will just write down. And the blue is the flow value. Right? So this is another example. So you can check individually that each edge The flow value assigned is at most the capacity and at least 0. Yeah. And flow conservation, you can check. At A, you have 5 coming in and 5 leaving. At B, you have 7 plus 2, 9 coming in and 5 plus 4, 9 leaving. At C, you have 4 coming in and 4 leaving. D, you have 3 coming in, or 3 plus 3 coming in and 6 leaving. E, you have 5 plus 2, 7 coming in and 3 plus 4, 7 leaving. F, you have 2 coming in and 2 leaving. So flow conservation is also met and at all the vertices. What's the total flow here? What's the total flow value here?
12.
It's 12, right? So if you look at the total outgoing flow from S, it is 5 plus 7. Or you can look at the total incoming flow at T, it's 6 plus 4 plus 2. Both ways, it's 12. Right? Again, when I'm not indicating anything, I mean, so for instance, SC is not carrying any flow. Okay. So value of flow is 12. Cut, you can have many cuts. So one cut is this that I've indicated, where the green part is S and the purple part is T. What is this? What is the, okay, I think you can already see it, but what is the capacity of this cut? So you have to look at all the edges that are going from S to T. So you have this 4, you have 5, you have 6, you have 9, and you have 9. So 4 plus 5 plus 6 plus 9 plus 9, it's 33. There is this edge that is coming from T to S, which we don't count. So quick question, can we push more flow in this picture above? Are there better flows here?
At least one we can increase.
Yeah, how we can increase?
From S to C, if you increase it by 1, then C to E increase by 1, then E to T increase by 1.
Correct. So what you're suggesting is S to C to E to
No, E
S
to
to C
T.
to E to sorry.
T.
Yeah. So basically, you are saying push one flow, 1 unit of flow in this path, get a flow of 13. Correct. Anything else that we can do?
Wait. Yeah, one more we can push from S to T1, C to E, E to F, and F to T.
So this is what you're saying, right?
Huh.
But through this path, how much more can we push? We can. There is a lot of leeway, right? So here there is the
Two
entire
more.
capacity of 4 is unused. Here
Huh.
you have a capacity of 5 that is available. Here there is a capacity of 4, and here there is a capacity of.
So 4, I think we can push.
Yeah. So yeah, assuming we are starting from this picture and not considering
From the previous one. Huh?
Yeah. So maybe I'll just so yeah, another flow is basically blue, right? So here we push 4, and that 4 has to go 1 over here. So here we push 6, and here we push that extra 4. You push here. So just here it was 4, right? Yeah, 4. Just let's verify conservation at E. So it's 5 plus 6, 11 incoming, and 3 plus 4 plus 4, 11 outgoing. Okay. And finally,
one more we can push. From D to T, we cannot push anything because I think.
no, let me complete this first. Sorry.
That's fine.
So 6 to 8. So now 6 over 8. So this is fine. So this is now has a flow value of 16. And you're saying one more we can push?
S to A to E, E to T.
So you find this path. This, there is one more you can push. Here, this is unused as of now. Here also we can push. Okay, so let's do that. So it was 5 here, right? So it becomes 6 here. And here it becomes 1. And 12 is incoming. So here it was 5 over 5, right?
Hmm.
Okay, so here the total flow is now 6 plus 7 plus 4 is 17. Okay. Okay. Yeah, that's good. What can we get a smaller cut with smaller capacity? Just so that we can spend some time on the cut as well. Can we get a cut with smaller capacity? Maybe let's replicate this figure. So the cut that we showed earlier had a capacity of 33. Can we get a like any simpler cut, any smaller cut? What if we do this? What is the capacity of this cut? Where ABC go with S. So it is 3 plus 9 plus 6. So it's a lot. It's 12 plus 13, 25, 27. So this is a better cut. This is capacity 27.
So if you take like very few nodes in one of the set.
That's okay. The only thing is that S should be on one side, T should be on the other side. So we can, even this is an ST cut. So this has capacity how much? 8 plus 6 plus 8 plus 7 plus 4 is 9. So this is an ST cut. So where you just have S on one side and you have everything else on the other side. This is an ST cut.
So 19.
This is 19. Yeah. So this is set S, this is set T. So this has capacity. It's 19. Yeah. You could have other cuts also, I think. Okay. Is it clear what the definition of the flow and the cut and the max flow and the min cut are? Okay. Okay. So intuitively, what do you feel like? Suppose you have a flow and a cut. So, okay, so now so this cut itself, does it tell us something? Let's say that we have a cut of capacity 19. What does this tell us? Can we send a flow of 20 through this flow network?
This particular cut is not possible because there's only source. So source entire capacity is 19. So we cannot send more than 19.
So in this particular flow network, we cannot send more than 19 because the source can only send at most 19. Like the capacities itself are 19, so you cannot send more than 19 flow. So the total flow value can be at most 19. The maximum flow is at most 19, maybe smaller. But this is true in general. Like even if the cut were something else, this is true. In fact, I think there is a smaller cut. I think. Let me just try to find it. Let me see. I think there is a smaller cut. I'll just indicate it now. I'll not waste time to. let's say this is our S, and let's say this is our T. What's the capacity of this cut? Basically, you have 5 edges crossing from S to T.
Yes.
3 plus 3 plus 5 plus 4 plus 2 plus 5, 11 plus 6, 17. Okay. Now, can we have a flow of capacity, let's say, more than 17? I claim it's not possible. I claim that this cut prevents more than if a flow value more than 17 being sent from S to T, because the reason is this. If there is a flow going from small s to capital T, right, there is flow conservation everywhere. So even across this cut, the flow has to cross this cut and go, right? So the maximum flow that can go from this, the purple part to the green part is at most 17. So if there is a flow, whatever be the, like, however we are arranging the values, it has to cross this cut and go. But the maximum that these 3 vertices together, this particular cut can take across, can flow across the cut is 17. So it is not just because in this case it was a source vertex, so it so happened. But even in other cases, what I'm saying is that it is not possible that you can send more, because how are you going to send more from this side to that side? So it is like sort of the bottleneck that is happening here. Like you cannot send more. You may be able to send more from S, and maybe it comes over here into A, E, or whatever. But crossing over from the purple part to the green part is not happening. Is it clear what I'm saying, at least intuitively?
Sir,
Is it
so
clear what I'm saying? Is the question.
yes, sir. But I have doubt that so
Ah.
we should consider all the cuts such that after the removal of the cut, one component should contain S and other component contains T.
Can you please repeat the question?
So what I was thinking, are we considering all the cut or our cut should be such that after the removal of the cut, the components we will get 2 components, right?
Okay.
So one should contain S and other should contain
Correct.
T.
Correct. Yeah, these are the type of cuts that we are interested in.
Okay.
Yeah. So this, I think in the definition I mentioned this. A ST cut is a partition of vertices in 2 parts, capital S and capital T, such that capital S contains small s, capital T contains small t, and these 2, capital S and T, form a partition of all the vertices, meaning they are disjoint and their union is the entire set of vertices. Okay, so what I want to, again, if there are questions, please feel free to stop and ask. What I'm saying is that this cut, the capacity of this cut being 17, prevents any more flow from being sent. Because if you divide these two, the set of vertices into these 2 parts, and you just look at these crossover edges are limited in their capacity to carry more from this side, the purple side, to the green side. So which means any flow from S to T is bounded by this cut. It is bounded by all the cuts, but it's also bounded by this cut, right? So what we are saying is that if we'll formalize whatever I'm saying just now. We are saying that suppose G is a flow network, let F be any feasible flow. Okay, so maybe I'll just write it here. Let F be any feasible flow, and let ST be any ST cut. Okay. F is any feasible flow, and ST be any ST cut. Okay, then in that case, the value of the flow is at most the capacity of the cut. So F is any feasible flow, and ST is any ST cut, then the value of the flow is at most the capacity of the cut. Okay, so we are basically, it's whatever I'm saying is that what I just said over here. This is one cut, and I'm saying that you cannot send more flow than 17 because any flow that we send will be limited by this cut. So this is the same thing. If you give me any cut of any capacity and any flow of any feasible flow, the flow value has to be bounded by the cut value. Okay, so, and in particular, this works for any flow and any cut. So I can even take the maximum possible flow, which I define to be the max flow, and I can take the smallest possible cut, which I call the min cut. So even if I take F to be the maximum flow and ST to be the cut of the smallest capacity, even then this should be true. So which means the maximum flow is also upper bounded by the smallest cut. Is the statement clear? Is the statement clear?
Yes.
Okay, thanks. So now what follows, since I have like say maybe like around maybe like at most like 12-13 minutes more, I'll quickly go through the proof. The proof is this long because I wrote down each and every step, but it's not that difficult. So the value of the flow, this is the definition of the flow, right? The total outgoing flow from S minus the total incoming flow to S. Then what we do is we not just S, we add all the other vertices, right? So here it is written only for S. Now I'm adding all the other vertices, but then for all of the other vertices except small s, because of flow conservation, we are just adding zeros. For any other V, F of this is the total outgoing flow, this is total incoming flow, this is just zero. So basically the summation, we are just adding a bunch of zeros. Okay. And this is the same thing, I just remove the bracket. And here I am, so this is all W. So now I am only like anything that is inside S, I am removing from here. Like S to S edges I am removing. And here also S to S edges I am removing. So in this step, all that remains is S to T things. S to S things are added both here as well as here. So I am removing them. And here I'm just noticing that whatever is not in S is in T. So we have this, right? And okay. So yeah, so it's not very difficult. But I'll just quickly go over because I don't want to spend that much time. And here you have two quantities, this quantity as well as this quantity. So this is a positive quantity and this is minus another positive quantity. So A minus B is basically at most A. So basically I just dropped this, right? So this is the first. So here we have a less than or equal to, and it would be the first term. And here we have another less than or equal to, because the flow at each edge VW is upper bounded by its capacity, right? By the definition of what the flow is. So this is upper bounded by this. So you have this is at most this. But what do we have here? What we have here is, so what we have shown here is for any flow F that is feasible and for any cut ST, the value of the flow is at most the capacity of the cut. Is it clear? Am I audible?
Yes, you are audible.
Yeah, I got a pop-up saying something wrong with the internet. That's why I just double checked. Any questions on this statement? Like, it's okay if you don't follow steps of the proof, but at least the statement should be clear. So F is any flow, ST is any ST cut. The value of the flow is at most the capacity of the ST cut. Things are clear?
Yes, sir.
Okay, good. Okay, now one thing I want to ask is, so we have an inequality here. The flow is at most the capacity of the cut. But in fact, in both our examples, here we found a cut of value 17 or capacity 17, and we actually found a flow of value 17. In the previous example, we found a flow of value, this is not the same example. We found a cut of capacity 15 and we found a flow of value 15. Correct? In both the cases, we were able to find a flow which is equal to the capacity of a cut. So the question is, when does that happen? Does it so happen that a flow value equal to the cut capacity? Right? Is the question clear? Is the question clear?
Could you repeat it?
We want to know when is the flow, when is it possible that this inequality is going to be an equality? This inequality, F is at most ST, is it going to be an equality? So if you look at the steps over here, there are two steps where we have less than or equal to, this one and this one. So when we have equality, both of these will be equal to. Right? So when F is equal to ST, both of these will be equal to. Let's try to understand when will both of these be equality. Okay, maybe inequality 2 is easier to see. This inequality is an equality when for all the edges VW that is crossing the cut, for all the edges that are crossing the cut, the flow value is equal to the capacity. Right? That is when inequality 2 will be actually equality. And inequality 1 is basically how did we get inequality 1? By ignoring this negative term. So this will be an equality when the negative term is basically not there, which means that this sum is basically 0, meaning that for all the edges from so this is UV where U is in T and V is in S. So for all the edges from T to S, right, the flow value is 0. So what we are saying is that when both the inequalities are tight, inequality 1 is tight, which is the thing that I just said. When there is no incoming flow from any edge that goes from T to S. Right? No incoming flow from T to S. That is when inequality 1 is tight. And inequality 2 is tight when for each edge going from S to T, the edge is saturated, meaning it is carrying. Okay, there is a small typo here. What I want to say is it is happening when for each edge that goes from S to T, the flow value is equal to the capacity. Right? So maybe we can just check. Let's see, in here, does it happen? So our cut was something like this. And if you look at the edges that are crossing the cut, this is tight, this is tight, this is tight, this is tight, this is tight. And there is no edge that is coming the opposite way. So inequality 1 is trivially true. And in the other example, yeah, this was our cut. This was our cut, which is, so if you look at it, this is the cut. These two edges are tight. And this edge is carrying 0 flow. Right? So in both these examples, we are just verifying our statement. Right? So this is when we get the flow value equal to the ST value. Okay. So I'll just say one final, maybe for a few minutes, and then I'll stop. Okay, Rajesh? Like I can take up to 5 more minutes?
Yes, you can take, yeah, please.
Yeah. So we saw that in a flow network, the maximum flow is at most the minimum cut, right? That's what we said here. Maximum flow is at most the minimum cut. What is actually true is that in both of our examples, we saw that the maximum flow and the minimum cut were equal, right? Because you cannot get a better flow or better cut in both of these examples because there is a matching value for flow and cut. What is actually true is that in any flow network, the maximum flow is equal to the minimum cut value, right? So that is what I wanted to talk about, but unfortunately we are out of time. And to show this, basically we will give a kind of algorithmic process by which whenever we are not at the maximum flow, we will find basically what we'll do is remember in our discussion we earlier, let's say over here, we said that over here we said that okay, now why not we send an extra flow like this or extra flow like this. So basically what we'll do in the algorithm is to find such possibilities of extra flow, and whenever we are not at the maximum, we'll say that we'll find such paths and push the extra flow. And the only way we'll not be able to push the extra flow is when these two conditions happen. When for all the basically we'll get a set of that will naturally result in a cut where the algorithm will identify the cut where all the edges crossing from S to T will be saturated and all the edges crossing from T to S will be empty. And this kind of algorithmic process will is how we prove the theorem. But since I do not have time, I will not get into the proof of this. But it's something very helpful and nice to know that in any flow network, maximum flow is equal to the maximum minimum cut. So basically, this is what I just said. We'll find like such paths where you can push some extra flow and you carry it. And then at the end, I want to talk a bit about what is the running time of this algorithm. So in general, the algorithm is not very efficient, but there are some heuristics, there are some rules that you can apply on how you find these paths that in such a way that the algorithm becomes efficient. Okay, so that's all I wanted to say. So overall, we saw in general algorithms, how to measure the complexity of algorithms by asymptotic notation, how to represent graphs in a computer. Then we saw basic traversal algorithms, DFS and BFS. And we saw applications of DFS like topological sort, connected components, strongly connected components. We saw BFS and Dijkstra's, which are shortest path algorithms. And then we saw the max flow min cut. We saw the max flow is less than or equal to min cut. We also said that it is equal, but we didn't see the proof. But it's a nice proof. So whenever you get a chance, I'll share the notes and then you can have a look at it. With that, I think I'll conclude my session. If you have any questions, I'll be happy to answer. Thanks. Looks like nobody has questions. Shall we wind up, Rajesh?
Okay. So stop recording.